In the long division algorithm I learned, we'd find out how many times the divisor goes into the first term of the dividend, or if the divisor is higher than the first term of the dividend, then how many times it goes into the first two terms. Then we'd put that number at the top of the division sign and subtract the product of that number and the divisor. And we more or less repeated that process until all the terms of the dividend were exhausted. The whole process was quite rigid. But I discovered something I would say is pretty shocking, at least to me when I first noticed it. It really doesn't matter whether or not you pick a number that goes into the first term or the first two terms. You can pretty much pick any number you want and multiply the divisor by that. Pretty much any number. Really opens up a lot of freedom. To explain why we can do this, we have to have some sort of idea of what long division with this algorithm is. The heart of this algorithm, and division in general, is subtracting the divisor from the dividend repeatedly and keeping track of how many times you subtract. You can either subtract the divisor once each time and count how many times you subtract, which is very time consuming, or you can subtract groupings of this divisor, which significantly cuts down how long it takes you to find your answer. If we take a typical long division problem with this algorithm, which I believe is called the Henry-Briggs algorithm, and expand it out a bit, it helps you see how long division is how I just described it. In this example, you see how when you subtract 6, you're really subtracting 1,000 groups of 6 at once, then 300 groups, then finally 8 groups. We keep track of how many groups of 6 we used at the top of the division sign, and we do the actual subtraction of the groups below, exhausting what's left until we can't subtract any further. The typical division notation we use leaves out these details, so we don't have to write so darn much with each problem. Now in this slide I show how if I use the same dividend and the same divisor, I can still get the same quotient, choosing different numbers to multiply the divisor by each time I subtract. Crazy, isn't it? Especially if you're used to having to re-guess what to multiply the divisor by in a subtraction step because you initially picked the quote-unquote wrong number. So now we see how we keep on subtracting whatever random divisor product we want from the dividend until we get down to nothing left to subtract. It's like the Price is Right, where you can go as high as you want in each step as long as you don't go over. But here's another fact that's going to shock the world, and nobody can reveal it better than the shock master.
You want a piece of me?
Actually, he didn't go over very well and sort of fell flat. So I'm just going to tell you this shocking fact myself. You see, unlike the Price is Right, you actually can pick a divisor product that goes over the unsubtracted part of the dividend and keep continuing the algorithm. Let me show you. Going back to our 7,850 divided by 6 example, let's suppose when we got down to 752 of the dividend remaining left to get rid of, we went way over by picking 200 to multiply 6 by. Well, we can still continue even if we go over it even further a second time. But eventually, we'll have to go back by multiplying a divisor by a negative number, that being negative 100 in this case. But the process still, interestingly enough, works. I think that's enough shock regarding long division for one day. I first stumbled upon this idea when I was looking for a practical application for that worthless variable modular arithmetic I thought of a while back. And in that case, variable modular arithmetic is like working with a divisor that changes and is not constant. But I didn't see it lead to anything interesting, and I don't want to go into that here.